Okie dokie, good morning, chemists. We'll get started now. Why is my thing not working? Where's my screen? Did you? Nope. Give me a second. All right, well, the plan is for today is to finish up chapter 16 with some randomized practice questions to see if we're understanding what type of method we should be using to approach not only pH calculations but Ka calculations using the information given. Do we understand, are we working with an acid or a base? So which K expression is most appropriate to use? So we'll practice all of these to identify, are we working with an acid or a base? Should we use method 1 or method 2 for our ice table, where only method 2 is where we use an approximation? So there's a couple more slides in chapter 16 that we'll work through with these practice problems and approaching these questions, and then we'll take these skills to chapter 17 where we'll use them again, but expand on it, look at kind of some weird scenarios of what happens when we work with solutions and acids and bases in aqueous conditions, so dissolved in water. All right, so this will be on midterm 3, right? Yeah, and so I like midterm 3 because it covers weak acids, weak bases, and buffers. So it's really comprehensive. Thankfully, strong acids were on the last exam, so everything in midterm 3 are going to be weak acid, weak base systems. All right, so randomized practice questions. So ask yourself, am I working with an acid, a weak acid? If you are, then it probably makes most sense to work with the Ka expression. If you're working with instead a weak base, it makes more sense to use the Kb expression, all right? So remember how we can identify an acid, a weak acid versus a weak base. You know, we can have HA can be a weak acid, B can be a base, but if we think about the conjugate A minus, what is A minus? A minus is a base. So if you have A minus in your solution, you should be using a Kb expression, or if you're using the conjugate acid form of a weak base, then you want to use the Ka expression. So not only are we just working with like the charge neutral species, but their conjugates as well, but the approach is exactly the same. All right, and then the two methods, the ones that I affectionately call the Sudoku method, where typically you calculate Ka, meaning with the information given, usually they give you the equilibrium line. They give you a hint at the equilibrium line. Either they tell you the H plus concentration at equilibrium, so essentially they tell you what the pH is. That is a hint at the equilibrium line, or they can give you percent ionization. And we'll do an example of that. So if you're given either of those things, you will not make an approximation. You'll actually use this piece of information to fill in the rest of your ice table to calculate the missing piece. And then finally, method 2, the quadratic, where you are given initial concentration, you're given K, and you have to calculate the equilibrium line. So method 2, we're always calculating the equilibrium line, either H plus concentration or OH minus concentration to calculate pH or percent ionization. We almost always use the approximation, and so when you fill in your ice table, what it looks like is you get x squared over initial concentration equals whatever K you're given, where x can either equal H plus concentration or hydroxide. So let's work through these, figure out, is it an acid or a base? Is it method 1 or is it method 2 where we make an approximation? All right, there's the demo. All right, so this first one, what is the pH of a 0.1 molarity HF solution at 25 degrees Celsius? There's the Ka for HF. If you're given a Ka for something, or a Ka or Kb, you can basically automatically assume that that is a weak acid or base if you're given a K value, versus if like we're working with HCl. Will HCl ever have a K value? HCl is what kind of acid? Strong. So does it have a K value? No. No, so if you're not given a K value, like in the context of this question where it's asking you what is the pH, we can go ahead and understand that that is probably a strong acid or strong base. So HF is definitely a weak acid because a Ka is given. Okay, so is HF a acid or a base? It's a acid, perfect. So which K should we use? Ka, and perfect, we are given that. So since we're given the Ka for an acid, it makes sense to write out the expression, the actual chemical reaction for a acid dissociation. So we can take HF, dissolve it in water, we get H plus and its conjugate, oh, I won't do acid, I won't do A, F minus. We get its conjugate base, all right? Looking at this question, what do we think it is, method 1 or method 2? Are we going to make an approximation here? Let's see if we make an approximation. So as always, you know, fill in your ICE table with the pieces of information given. So since we are trying to calculate the pH, what we want is whatever value is at equilibrium for H plus. That's our goal. We need to figure out what this number is. So let's fill in the rest of this information. So 0.1 molarity HF, where will that go in our ICE table? In which line? I, C, or E? It's going to go in the, anyone? Initial? Change? Give me some indication that our brains are on right now. Where is that 0.1 molarity going to go? In which line? Initial, thank you. So 0.10 molarity, whatever sig figs, goes in HF. We have none of the other stuff. So which way does this reaction have to go? Forward, so minus X, plus X, plus X. And so we get at equilibrium. There is 0.1 minus X of the HF, that's intact, but then X amounts of H plus and F minus. As always with ICE tables, we want to take that E line and put it into our Ka expression. Ka is equal to products over reactants, and so I'm just going to go ahead and put those terms into that Ka expression. So X squared over 0.1 minus X, and set it equal to the Ka value that's given. So 7.2 times 10 to the negative 4, perfect. All right, can we solve this? Can we solve that? Yes, there's just one term, but as written right now, does it require the quadratic? Yes, it does. Do we want to do the quadratic? No. So should we make an approximation? Yes. So this is why we can do the approximation. X. Is X going to, when we solve for this, is going to be a big number or a small number? When you look at this ICE table and the value of K, the magnitude, is this reaction going to go forward that much? No. No, it's actually really close to equilibrium already because Ka is so small, meaning that there's not a lot of product but a lot of reactant present. So this minus X is going to be a really small value next to the 0.1 that it's connected to. 0.1 is a fairly big number. It's only 1 order of magnitude away from 1. So that's why we can make this approximation where the denominator, we can just get rid of that minus X, and then it's very simply just take a square root. All right, and so when you do that, when you solve for X, we get that X is equal to 0.00849 molarity, but it's the molarity of what? H plus. How do we know that it's the molarity of H plus? That's what it says in the ICE table, or you can think I used a Ka value. Acid means we produce H plus. So that X value is H plus concentration. Go ahead, take the negative log of that, and you get a pH is 2.09. All right, so let's check our intuition. What did we put in water, an acid or a base? An acid. And then what is our pH that popped out? Acidic, perfect. So is your brain satisfied with that answer? Yes, so then we can move on. Because if they don't match, then something probably went wrong. Either you didn't use the right Ka value or K value or misrepresented what X was in your calculation. All right, so this is a method 2 pH calculation where we make the approximation. We're calculating pH with a given K value and in a given initial conditions. What you're going to see a lot is this type of form, x squared over initial concentration equals K, where x can equal many things. So hopefully, you know, if I gave you a laundry list of pH calculations, hopefully you don't actually have to write the ice table every single time. You'll recognize it's going to be x squared over initial concentration equals K. You just need to make sure you use the right ones. All right, next one. All right, what is the pH when we put 0.1 moles of sodium fluoride and dissolve it in half a liter of water? There's the Ka for HF. Okay, so we're given a Ka for HF, but are we putting HF in water? No. What are we putting in water? Its conjugate base. So we're putting its conjugate base in water. So when we put a conjugate base in water, our pH should be predicted to come out what? Basic. All right. So is it appropriate to use the Ka value ice table here? Nope. We want to use Kb. Yes. So we want to use the Kb. So I'm going to go ahead and calculate that. Kb, because this is a base, is Kw over Ka. So 1 times 10 to the negative 14 over that value that's given. And so we get Kb for A minus, because that's what we're putting, or I guess not A minus, it's F minus. What we're putting in water is the conjugate base and not the acid. So 1.38 times 10 to the negative 11. All right, so that is what Kb is. That is the number that we'll move on and use. So is it appropriate to write a Ka expression for our ice table? No, we want to write the Kb. So let's go ahead and write the Kb expression, where F minus reacts with water. I need that water there because bases, Lewis bases accept protons. So it's going to steal a proton from water to make HF again, and then we're left with that hydroxide that is indicative of a Kb expression. Go ahead and fill in our ice table. Right? And so since we're calculating pH, we want to know what the heck is the number under OH minus concentration at equilibrium. So in this case, we'll have to calculate POH, then pH, but no big deal. And so let's fill in the rest of this ice table. What number is going to go in our initial line under F minus? Is it going to be 0.1? Yeah, it's 0.1. So 0.1 moles goes in the ice table. Nope. What is the unit that our ice table needs to be in? Molarity. So what is the actual number that needs to go in that I line? Not 0.1. It's actually 0.2. Yes, 0.2 molarity, because the concentration of, not HF, of F minus initially is 0.1 moles over 0.5 liters, half a liter of water. So that is equal to 0.2 molarity. That's what's going in our initial line. So there's another way we can ask the question. I don't want an amount. There we go. 0, 0. Okay, so there's our initial conditions. Which way does this reaction have to go? Has to go forward, so minus x, plus x, plus x. Am I just ignoring water? It's not in the equilibrium, but it's still there. It's still being consumed a little bit. I just don't care about it. All right, so then add up our columns. So at equilibrium, we have 0.2 minus x of F minus, x of HF, and x of hydroxide. Does this look familiar? Yes, it does. So this E line always goes into K, but this time it's going into the Kb expression because that's what we wrote. We wrote a Kb equilibrium. So at equilibrium, we're going to have x squared over 0.2 minus x. This is equal to Kw over Ka, which is Kb, and we already calculated that to be 1.38 times 10 to the negative 11. So we already have that number. All right. So can we solve this with a quadratic? Yes, but do you want to do the quadratic? No. So what is the most appropriate approximation we should make? Let's get rid of that minus x in the denominator. All right. We can do that because KB this time is a really small number. So with this approximation, what we get is it simplifies to x squared over 0.2 equals 1.38 times 10 to the negative 11, and that's so much easier to solve, especially in exam conditions. So you solve for that, and you get that x is equal to 1.67 times 10 to the negative 6. But this is the concentration of what? OH minus this time, because we used a KB value. All right? So when we negative log this number, we don't actually get pH. What do we get? We get POH instead. So we get that POH is equal to 5.76. All right? And so then we're just 14 away from pH. pH is just 14 minus that, so 8.28. So there is our pH. So let's check our intuition. We put what into water, an acid or a base? A base, and the pH that came out is basic. Okay, good. So that satisfies my brain, so I can move on. Because if you just, if you assumed that X was H plus concentration and you stopped right here at POH, right, and you just thought, oh, okay, my pH is 5.78. That is what kind of pH? That's acidic. Yeah, and so hopefully you can reflect on that and be like, okay, somewhere I went wrong if I got a pH that's acidic. You don't want that. All right, so there is another method too, where we use the approximation, the ice table, but minus X is really small, so we can neglect it. So hopefully, I think at the end, I have a bunch of these that we can do, and hopefully you don't have to write an ice table every single time. Okay, but sometimes you do have to write an ice table, like in this one, to help you understand what's going on. All right, so we have a 0.04 acid solution. It is 2.2% ionized. Calculate equilibrium concentrations of everything and Ka. Yikes. So let's just go through the same method. What are we putting in water? An acid or a base? An acid. So it probably makes most sense to write a Ka expression, and it looks like we're solving for Ka. I'm just going to write a generic one. Ha goes to H plus A minus. So I need to calculate Ka, which is products over reactants. But all of these concentrations have to be the concentrations that are at equilibrium. So that equilibrium line. If I know all of those values, then I can stick it in and calculate what Ka is. All right? So let's make our ice table here. This 0.04, that is our initial concentration of our weak acid. We have none of that. So hopefully you'll see that our ice table looks very, very similar to the previous two. This reaction still has to go in the forward direction. And so at equilibrium, we're going to have 0.04 minus X of HA, X amount of H plus, and X amount of the conjugate base. Looks exactly the same. But the only difference in this question is we're not actually solving for X. That's what we did in the previous two, the pH calculations. We want to figure out what Ka is. And so there's one last piece of information we did not use yet that's going to give us a hint at the ice table. And what is the piece of information we didn't use yet? 2.2% ionized, yes, so we didn't use that yet. So remember what percent ionization is. That is one of the equations that you get on this exam. Percent ionization is equal to your H plus concentration at equilibrium over your initial concentration of your weak acid. Or if this is a base, then it would be hydroxide over initial base concentration. So that is percent ionization. So we know this value, we know the percent ionization, and we know how much acid we started with. So since we know two of the variables here, we can actually calculate what is the H plus concentration at equilibrium. This question is really no different than if I just gave you a pH value directly, because pH tells us our X value. Percent ionization, as long as we know what the initial concentration is, also gives us our X value. So this number that we're solving for actually is X. So putting this together. So 0.022 equals the X value, because again, that is H plus concentration, over 0.04 molarity. This will tell me what is the concentration of H plus, how much of this acid actually ionized. And so if we go ahead and solve that, we get that X is equal to something. 0.00088 molarity. Is that right? Is that right? Yeah, okay, perfect, thank you. All right, so that is the concentration of H plus, and we know what X is now. Perfect, so we can just go ahead and plug all of those values in, get the equilibrium concentrations of everything. So X is equal to the H plus concentration. It is also equal to the conjugate base concentration, so we have those two. And so to get the concentration of HA at equilibrium, we actually have to do the subtraction. So do not make an approximation here. All right, I know you want to, because we've always been just neglecting the minus X, but we know what X is now. So if you make an approximation here, you're just being lazy, because we know what X is, so just do the subtraction. So we see that 0.04 minus 0.00088, we get that the concentration of HA is 0.03912 molarity. So there are all our equilibrium concentrations. So see, it did change a little bit. It's not 0.4. Some of it did ionize and go to products, so it's a little bit less than that. And so now that we have all of the equilibrium concentrations, we can go ahead and calculate Ka. Ka is equal to X squared over 0.4 minus X, or just plug in all those numbers we just solved for. So 0.00088 squared, again, do not make the approximation. You know what X is, over 0.03912 molarity. And so we get, what's my answer? Ka is 2 times 10 to the negative 5. Okay? All right, so that is a method 1 ice table where percent ionization gives you a hint at the equilibrium line, and you can fill in the rest and calculate what K is. All right, so let's just do one more of these. All right, we have a solution of acetic acid. There's its pH. What is its molarity? That's written on the bottle. All right, so you go to lab. You know you have a acetic acid solution at 25 degrees Celsius. You put your pH probe in, you calculate its pH, or you measure its pH, and we can figure out what concentration we should write on the bottle here. So let's write our ice table. So what are we putting in water? A acid, so we should write which expression? Ka, yes. So I'm just going to write a generic one. HA ionizes to H plus and its conjugate base. We got our ice table, all right? So we are calculating the concentration written on the bottle. See how in all the other questions, the concentration given, we always put in the I line, in the initial line. This time we're solving for the initial concentration. We're solving for that I line. So I'm just gonna call the initial concentration N, because that's what I'm solving for essentially here. I'm solving for N. But let's still go ahead and do the ice table as normal, as if we knew what N was. We're still gonna lose a little bit of HA, gain a little bit of our products. So at equilibrium, we're gonna have N minus X amount of HA, X amount of H plus, X amount of A minus. So this looks exactly the same as it always has. So we put those values into our Ka expression, so it's X squared over N minus X. And I actually gave you Ka this time, 1.8 times 10 to the negative 5. So, as is, can we solve this? No. Why? There are 2 variables. So we need to get rid of one of those variables. So what piece of information did we not use yet? pH. So pH is going to tell us which of those variables, N or X? X, because pH tells us, pH is our H plus concentration at equilibrium. Not the value, but we're just one step away from that. So if pH is equal to 3.45, that means X, or the H plus concentration, is equal to 10 to the negative 3.45. And so you plug that into your calculator, and you get that X is equal to 3.55 times 10 to the negative 4 molarity. That is what X is. All right, that's X. So we just plug that into our Ka expression now. All right, and then we can solve for N. Should we make an approximation? No, don't make an approximation. We know what X is. And then we see that the variable that we need to solve for just is in one spot. So don't make the approximation. 3.55 times 10 to the negative 4, that is squared over N minus 3 point, same number, 3.55 times 10 to the negative 4 equals 1.8 times 10 to the negative 5. You can solve for that. N is just in one spot. So moving things around, we can rewrite this as 3.55 times 10 to the negative 4 squared over 1.8 times 10 to the negative 5 equals, I'm just putting the denominator on the other side so I can isolate N. All right, so we get something like that. What did I do? No, I didn't solve it. Okay, so let's solve this. 3.55 e negative 4 squared over 1.8 e negative 5. So this side of the expression, 0.00700, equals N minus 3.55 times 10 to the negative 4. And so add that minus X value, negative 4. And we see that N is, yeah, something like that, right? Right there. 0.0073. Okay. So this question is really no different than the previous one. It's just we solve for a different variable here. All right. In the previous one, we solved for Ka. We got the equilibrium concentrations. But one additional way I can do it is give you a pH. You can fill in the equilibrium line, and we can solve for N if I give you Ka, or the appropriate K expression. All right. So no approximation needed there. All right. Okay. How do we feel about this? Yeah. Ask yourself these questions. Am I putting an acid? Am I putting a base into water? Which expression do I need to write out? Okay, so here are the strategies for calculating pHs and POHs. Remember, always be asking yourself, what am I putting in water? Is it an acid? Is it a base? And additionally, is it a weak acid or base, or is it a strong acid or base? So remember earlier, I know that this was chapter or midterm 2, but it's good to go over it because the idea is if I give you an HCl solution versus an HF solution, you'll actually approach these pH calculations differently because HCl is a strong acid, all right? So we can just assume that all of the acid concentration is your H plus concentration at equilibrium and go ahead and calculate pH. But if I give you an HF concentration, you're actually going to use the Ka value for HF, do an ICE table to calculate pH because HF is a weak acid and we need to follow its K expression. But HCl, on the other hand, is a strong acid. So an example, yeah, would be like HCl, nitric acid, chloric acid, perchloric acid. All of those things, you make an assumption that all of the acid you put into solution is H plus at equilibrium. Same thing with strong bases. If you put sodium hydroxide in water, we're assuming all of that hydroxide is the hydroxide at equilibrium. So you can go ahead and calculate POH and then get pH. A small little detail with strong bases, we can also have something like calcium hydroxide, all right? So if I give you a concentration of calcium hydroxide, the actual hydroxide is going to be 2 times that, all right? 2 times that, because 2 hydroxides for every 1 calcium hydroxide. So if you put 1 mole of calcium hydroxide in water, there is actually 2 moles of hydroxide there. But it's still the same idea. Then calculate POH, pH. Those are strong acids, strong bases. But you need to recognize when I give you something, is it a strong acid or strong base? Okay, so it's the weak acid systems that are harder, all right, and weak base systems. So let's say I give you a charge neutral weak acid. So this is, I think, this is chlorous acid, so this is a weak acid. So if I give you chlorous acid, this is an acid, so it makes most sense to use Ka. All right, so if you put an acid into solution, use the Ka value. If you go ahead and do the pH calculation in the ice table, it's going to be x squared over initial concentration of the acid that's given equals Ka, where x is equal to H plus concentration. So you can go ahead and calculate pH from there. Versus if you put a base into solution, so what is this? Methylamine. All right, this is a weak base, so it's most appropriate to use a Kb expression instead. Where then if we go ahead and calculate the pH of this base, weak base, it's still, the ice table is still going to be x squared over initial concentration of the base, but it's equal to Kb now, where x is equal to the concentration of what? Is it H plus still? Nope, it is hydroxide concentration because we used a Kb expression. All of the pH calculations will take this form. It's just the x identity changes and Ka versus Kb, you need to make sure you're using the right one. So if you get hydroxide concentration, you can calculate POH and then pH. Right? Okay, the last ones, and these are the harder ones, is, okay, what if I give you the conjugate of a weak acid, meaning the conjugate base of a weak acid? So this is not chlorous acid, this is sodium chlorite, right? So A minus is a weak base. So we actually want to use Kb instead here because A minus is a weak base. But will I ever give you Kb of a conjugate base? No, I will give you the Ka of the conjugate acid, but you're always just one calculation away from getting Kb of that conjugate base. You'll probably be given Ka, so you have to use Kw to solve for Kb. So when you do the pH calculation, it'll be x squared over initial concentration of A minus, but this is equal to Kb. X is going to be equal to hydroxide concentration because you used Kb, so then you calculate POH, then pH. All right. Okay, lastly is what if I give you the conjugate of a weak base? So Hb plus is actually an acid, so you want to use Ka. But I will never give you the Ka of a conjugate acid. I will always give you the Kb of its typical base form instead. But again, you're just one calculation away from solving what that is. And so since we used a Ka expression, Ka will be equal to x squared over initial concentration of the conjugate acid. And of course, I'm just doing the ice table, but using the approximation, because all of these take on the same form, where x is going to be equal to the concentration of what when you solve for this? H plus, yes, because we used Ka, and so you can pH that directly. Okay, so that is what you do, depending on what substance you're putting into water, all right? These are all method 2s, so using the approximation. This is, I give you a concentration of a substance, I give you the K value for it, and I ask you what the pH is. So that's what this very last slide is. Tell me, how are we going to calculate the pH of all of these things? So I give you Ka values of some stuff. I give you some Kb values. So we need to decide how are we going to calculate the pH for all of these. All of them have the same concentration. So let's see if we can't understand which, how we'll set up the pH calculation for all of these. All right, so here is the Ka for HClO. We have a Ka for benzoic acid. We have a Kb for ammonia and a Kb for trimethylamine. All right, so what is this? An acid or a base? An acid, so which expression should I use? Ka. Did I give you Ka for this? Look at your slides. Did I give you Ka? Yes, I did. Perfect. So we know that value. So when we solve for this, it's going to be x squared over 0.1 molarity. We can solve that easily. But when we solve for x, what is the concentration? Or sorry, x is the concentration of what species? H plus, because we used Ka, calculate pH. So that's how you'll calculate the pH for that first one. And we are given Ka. What about 0.1 molarity ammonia? What K expression do we want to use? Kb, because ammonia is a base. Did I give you the Kb of ammonia? Look at this. Look in the corner. Did I give you the Kb of ammonia? Yes, I did. So we don't have to do anything special. We can go ahead and say, okay, x squared over 0.1. But when we solve for x, it's the concentration of what? OH minus. Perfect. So then you just have to POH, then pH to get the pH. All right. Next one, sodium hypochlorite. What is that? Is that an acid or a base? That is a base, so I need to use the Kb expression. But did I give you the Kb of sodium chlorite or sodium hypochlorite? Look over here. Did I give you any sodium hypochlorite? No, I didn't, but I did give you what? The Ka of the acid form of it. So I didn't give you Kb directly. So we're going to calculate it by using Kw. Kb is Kw over Ka. I did give you Ka. So we'll have to solve for Kb here. And then this will be equal to x squared over 0.1 again. But when we solve for x, it's the concentration of what? H plus or hydroxide? It is hydroxide because we used a Kb value, and then again, you'll POH, then pH. All right, the next one. What is that? Ammonium chloride. Is that an acid or a base? That's an acid, so we're going to use Ka here. But did I give you the Ka for ammonium? Nope, so what are we going to use? The Kb for ammonia. So we can go ahead and calculate that. It's Kw over Kb. I know what Kb is. Kw is a constant. And then this is equal to x squared over 0.1, where x is equal to the concentration of what now? H plus, because it's Ka. So we can just solve for pH directly. Perfect. All right, next one, 0.1 molarity. What is that? Perchloric acid. Did I give you a K value for perchloric acid? Yeah, so how are we going to, so no, I didn't. So how are we going to solve the pH for this? What's special about perchloric acid? It's an acid. It's a strong acid. See, I tricked you. I tricked you. All the last four were weak systems, but perchloric acid is actually a strong acid. So how are you going to calculate the pH of that one? Just plug it into pH. Yeah, we're just going to do negative log 0.1. And so this has a pH of 1 with 2 zeros. That's it, because that one's a strong acid. So no Ka needed there. Okay, I tricked you. All right, next one. This guy, 0.1 methyl or trimethylamine. What is that? It's a base. Did I give you the Kb of that? Yes, perfect. So it's just x squared over 0.1, and we're ready to go. X is equal to hydroxide concentration because we used a Kb. Perfect. All right, what the heck is this thing? Doesn't it kind of look like the one we just looked at? It kind of looks like methylamine. It looks like methylamine because it is with just an extra hydrogen on it, an extra proton. So this is the conjugate acid. This is basically NH4 plus. It has an extra proton on it, and it's attached to nitrate, but that is a charge neutral anion, right? So this is a conjugate acid. This is an acid because it's the conjugate of trimethylamine. So again, we'll do x squared over 0.1, except we're not given Ka. Sorry, I forgot. So we have to calculate it using the Kb value that is given. Right, so these are two acid-base conjugate pairs. When you solve for x, this is H plus concentration. Go ahead and solve for pH. All right, are you seeing it all come together? All of this come together, recognizing what are we putting into water. All right, you put benzoic acid into water. Which K do you use? Ka. Did I give you the Ka of benzoic acid? Yes, perfect. So you just x squared over 0.1, and then x is equal to H plus concentration. Perfect. All right, last one. 0.1 sodium benzoate. Which K do I use? K. B, yes, benzoate is the conjugate base of benzoic acid. Kind of like carbonic acid, right, is a weak acid, but carbonate is the anion. So if benzoic acid is the acid, benzoate is the anion form. And so that is a conjugate base. I didn't give you Kb of benzoate, but you can just calculate what it is using the Ka of benzoic acid, x squared over 0.1. X is equal to hydroxide concentration. Right, those are all the pH calculations. So you can test yourselves if you want. I didn't show the work here, but I have all of the actual pHs down here. All right, if you actually want to do all the calculations there. And so really the only things that are changing is, solving for X with different K values, either using Ka or Kb, but recognizing some of them are given, some are not. You would have to calculate some of them using Kw. All right, so that's all of chapter 16. So what does that mean about homework? It's due on Monday. Yes. It's a long one because it's all the weak acid, weak bases, but again, this is preparation for midterm 3. Chapter 17 is a really long one. It's a really long chapter. It's insanely long. And where we're going to look at all the weird scenarios with acid-base chemistry. So I'll introduce 2 more K expressions, the last 2. Yeah, we're still going to be working with acids and bases. So all these skills, when do you use Ka versus Kb? What do the magnitudes of Ka and Kb, what do they mean? All of those are important in these slides as well. Okay, so what are we going to learn about in chapter 17? Again, I said it's all the weird exceptions or weird K scenarios involving acids and bases. So in chapter 16, we just looked at solutions that were only a weak acid. Like I asked you to calculate the pH of acetic acid, all right, like a 0.1 molarity acetic acid. Or I asked you to calculate the pH of 0.1 molarity ammonia. So only a weak acid or only a weak base was present on the bottle in that solution. So we're still going to be using this, this equation, pH equals negative log of H plus concentration at equilibrium. But we're also going to talk about this new equation, the Henderson-Hasselbalch equation, where, well, what if I have both an acid and its conjugate base present in very large quantities in a solution? And that's what a buffer is. We're going to do look at titration curves and calculating the pH at every single point on this titration curve, right? And you're going to do 2 labs. You're going to do a strong acid, strong base calculation titration lab, and you're going to do a weak acid, strong base titration in lab as well. How we approach pH calculations for these are a little bit different, right? In previous titrations, you've always used an indicator to figure out are you at the end point or not, but we can also use pH to determine if we're at an end point or not. So let's do some exploring. Okay, so recall we just went over this, how to calculate pH or pOH. Recognize do you have a strong acid or strong base, weak acid or weak base, or the conjugates of those things. This is review. We just went over this. This is actually the same slide as before. All right, just kind of summarizing all of these. These ideas are very important in this chapter as well. So we're going to look at all of the weird scenarios and how to approach pH calculations for all of them. So let's look at this first weird scenario. What if we have multiple things in water? Okay, so we did this before in I think chapter 16, where I put like HCl and HNO3 into water. Both of those things are strong acids. So if you determine, okay, what is the total amount of H plus present if I have a mixture of two strong acids, that's how I calculate pH. This is a little bit different, where let's say we have, here's one example. If I have two different acids, so HCN and nitrous acid, all right? So the idea here is if you have two acids in solution, you want to pick the strongest one. The strongest acid is going to donate the most protons, and so we're going to assume that that substance is what determines the pH the most. In chapter 16, when we put two strong acids into solution, both of them fully ionized, so we considered both of them. But in these examples, one of the acids is usually a lot stronger than the other one, so we can ignore the other one and just consider the strongest acid. So if we look at these two acids here, which acid is stronger? Cyanic acid or nitrous acid? Which one's stronger? HNO2, yeah, this one's much stronger. So we're going to just pretend that HNO2, I guess, how do I want to say this, determines the pH. It's the one that's going to ionize the most. It's going to make the most H+, so we can just ignore that first one, right? This first acid, its Ka value is really, really small, so it's only going to donate a little bit of H+ and not affect the pH as much. So we're going to just ignore that first one and just assume that, okay, my acid solution just has this weak acid in it, and so we can go ahead and solve for it where it's x squared over 0.2 equals 4.6 times 10 to the negative 4. Right? We're just assuming that the solution is just nitrous acid, and you can solve for x. Did I write it down? I probably didn't. Nope, I didn't. All right, solve for x. Where's my calculator? 4.6 e negative 4 times 0.2. Take the square root of that. Okay, we get that x is 0.00959 molarity. That's H+, and then you get a pH of 2.02. All right. And so again, we're just assuming that nitrous acid, the strongest acid, is the one that dictates the pH here. All right, let's look at this mixture. All right, we have a mixture of HCl and acetic acid. How would we calculate the pH? Is there one of those species that's going to donate more protons? HCl, yes, HCl. Why is HCl going to donate more protons? Strong acid. So do we actually have to do anything with acetic acid? Nope, we're going to just pretend it's not there, right? Acetic acid just donates a little bit of H+, and it's not going to change the pH that much. So what we see here is that HCl is what's donating the protons. So how do you calculate the pH of this solution? Do we need to do an ice table? Nope, we just put that right into the pH equation. So negative log 0.1, I think the pH is 1. Perfect. So strongest thing wins here. All right, last one. This strategy also applies to polyprotic acids. So pretend I have this diprotic acid, H2A, into solution. I give you two different Kas, Ka1 for H2A and Ka2 for HA minus. It's taking off that first proton because that's also an acid. So when I calculate the pH of this diprotic acid, so I put 0.1 molarity H2A into solution. Which K value will I use, Ka1 or Ka2? Ka1. Do I have to do anything with Ka2? Nope, I don't, because this value is so much smaller. Also, HA minus isn't what I put into solution. I put H2A into solution, so I actually want to use Ka1. So simply to calculate the pH, it's going to be x squared over 0.1 equals the 1 times 10 to the negative 3. Solve for x, you get, this is H+ concentration. What is it? Is it 0.02? Yeah, so it's 0.01 molarity, and so you get that the pH is 2 for this one, right? So strongest thing always wins. when you have a mixture of things. Keep this in mind when we're going to look at some other pH calculations where it's during our titration, there's always going to be a mixture of things. And so this strongest things wins. We can typically ignore the weakest substance will come up again. All right. Okay, so other weird scenarios. Ooh, this is my favorite slide in, I think, all of 1220. Okay. I trust you. All right. Hopefully you can solve these without doing any calculations. Okay, if I tell you we have an HCl solution, and that is the concentration, so 1 times 10 to the negative 3, what is its pH? What is it? 3. Did you put that in your calculator? No. Okay, perfect. 3. Because that's the rule of logs. Hopefully you recognize you've done enough negative logs that the integer value is basically the exponent that is in that scientific notation. Okay, what is this solution, acidic or basic? Acidic. Okay, does that match your intuition? Yes, good. So we can move on? Yes, okay, so let's do the next one. What if I have an HCl solution that's 1 times 10 to the negative 8? What is its pH? 8. Okay, is this solution acidic or basic? Basic? What's going on here? What did you put into water? An acid. So you're telling me that you put an acid in solution and it became basic. Are we satisfied with this answer? No. Yeah, you shouldn't be because this is wrong, right? That you can't put an acid in solution and it become basic. All right, so we've been making an assumption all along. Remember how I've always told you, okay, make the assumption that all of the HCl is equal to the H plus at equilibrium. We can do that when the concentration of the strong acid or strong base is really large. But there's actually 2 sources of H plus in an aqueous solution. Some of it's going to come from the strong acid, but there's something else in a solution that also contributes H plus, and what is that? Water. Water can contribute H plus, all right? So the idea here is that water can contribute some of that H plus because it auto-ionizes, it has that Kw. All along, we've been assuming that the total H plus in solution only came from the acid. But we can't do that when the acid concentration itself is really, really small, right? What is the pH of neutral water? Yeah, 7. So that means neutral water has what concentration of H plus? 1 times 10 to the negative 7, all right? So when we look here, HCl contributes 1 times 10 to the negative 8 H plus. See how these 2 numbers are similar? So when these 2 numbers are similar, we can't actually ignore water's contribution. But when we compare the first one, 1 times 10 to the negative 3, add 1 times 10 to the negative 7 to it. Does it change the number that much? It doesn't. So that's why for really, I guess, concentrated acid and base solutions, we were able to ignore water. So let me show you how to do it the right way, and this is for very dilute acid and base solutions, because we can't put acid in water and it become basic. This is absolutely wrong. All right, so let's do it. Okay, so the correct way to do a very dilute pH calculation, we need to use the ionization of water. And unfortunately, we can't make any approximations here. We actually have to solve for the quadratic. Okay, so this is what we do. We start with, since water is contributing, all right, we can't ignore Kw anymore. Let's start with the Kw expression for water. We have water, and it dissociates to H plus and hydroxide. This is Kw, and it has, a value 1 times 10 to the negative 14. So just like before, like when we were trying to calculate the pH of neutral water, we always said, oh, let's start with a random amount of H plus, of water. It doesn't matter how much because it never shows up in Kw anyway. But in this example, because we also have a very dilute acid, we want to put HCl into our ice table as well in the initial conditions. So HCl is actually going to contribute 1 times 10 to the negative 8 molarity in H plus initially. All right, so we're putting 2 things in that I line. A random amount of water and 1 times 10 to the negative 8 for coming from that strong acid. All right, based upon this, which way does this reaction have to go? You can predict it. It has to go forward because there's no hydroxide yet. All right, it doesn't matter that there's, stuff on both sides. There's no hydroxide, so we have to fill in that void. So we see that this reaction still moves in the forward direction, so minus x plus x. So at equilibrium, what we're going to have is a n minus x amount of water, 1 times 10 to the negative 8 plus x amount of H plus, and then an x amount of hydroxide. Like all ice tables, the E line goes into the Kw expression. So Kw equals 1 times 10 to the negative 8 plus x, that's H plus, times x, and that is equal to 1 times 10 to the negative 14. Okay. So when we solve for x, this is how we're going to calculate the actual pH of the solution, and hopefully it makes more sense where, oh, you put an acid in solution, it should become acidic, right? So what we want to do is distribute this x, so we cannot make an approximation here, right? We can't make an approximation. We actually have to solve for this. So when I distribute that x, it's 1 times 10 to the negative 8x plus x squared equals 1 times 10 to the negative 14. Move things around and put it into quadratic formula form. So 0 equals x squared plus 1 times 10 minus 1 times 10 to the negative 8x minus 1 times 10 to the negative 14. So I'm just putting all of the terms on one side, where it's, the A, B, and C terms. So we see here that A equals what? Once I have it in the right form, it equals 1. B equals 1 times 10 to the negative 8. And then C equals the constant on the end, but it's negative 1 times 10 to the negative 14. Right? So there is our A, B, and C terms. We can go ahead and solve for the quadratic to solve for what x is. And so when you do this, you get that x, the one that makes the most sense, the one that's a positive value, x is equal to 9.5 times 10 to the negative 9 molarity. All right? Okay. But that's the molarity of what? Of hydroxide. How do you know it's hydroxide? That's what x is in the ice table. Perfect. So this is actually the concentration of hydroxide, because that's how we defined it in the ice table. So when I negative log this number, I'm actually calculating what? pOH. So I get that the pOH is 7.02. Then what does that make the pH? 6.98. So there is the pH. Does that pH make your brain happy? What did you put into water? Acid. The pH needs to be acidic, all right? Before, when we made the assumption that all of the H plus is what contributes to H plus at equilibrium to calculate pH, we can do that when your acid concentration is really high. You can't do it when it's really small. Right? And so in this case, 1 times 10 to the negative 7 molarity HCl is small enough where we actually have to, negative 8, we have to consider it. And so finally, doing the full quadratic using the Kw expression, we can solve for a better pH that actually makes sense with our intuition. It does match our intuition. All right? We added acid to water. The solution should be acidic, not basic. All right. So yes, this required the quadratic formula, and I told you on exams, there's always an approximation that could be done to not need to do the quadratic. So this specific question would never show up on the exam, but this is how we could word it where technically you don't need to use the quadratic. So this actually came from the MCAT. I have an MCAT book that sometimes I look through to see what questions align with the content we're doing. So this is an MCAT question that I took straight out of the book. It says, what is the pH of a solution with HCl equals 1 times 10 to the negative 8? All right? And so what a lot of students will do is just do, oh, okay, HCl, that's the H plus concentration, pH equals negative log, 10 to the negative 8, so we get pH equals 8, and then the student moves on. Right? But what does that match your intuition? You put acid into water and it becomes basic, so 50% of students will circle 8, but is 8 the answer? It cannot be the answer, all right? So you can actually just think your way through this question, all right? It cannot be 8 because this water cannot be basic. What other one can we eliminate as well? 7.02, that one's also basic. And then what's another one we can eliminate? So why can't it be 7? Because that's neutral. You put in acid and water, the only one it can be is C. It's acidic. All right, so you could think your way through this, but this is kind of like a trick question, I guess, in that MCAT book. It's trying to get you to just plug in 1 times 10 to the negative 8 into that negative log expression, and then just move on. We can do that when HCl concentration is like 1 times 10 to the negative 4. All right, when it's really concentrated, we can do that. But once the strong acid concentration is really small, we can't. All right, oh yeah, so right here. I had that right there. Okay, so let's pretend that we have HCl is 1 times 10 to the negative 3. Do we need to do the whole ice table and KW thing if it's times 10 to the negative 3? No, because this number is real big compared to what water will contribute. So yes, we can go ahead and ignore it if the concentration is very large. But we can't when HCl concentration is very dilute. Right? So you could go ahead and do that. You could put this as your initial concentration in your ice table, but you'll calculate a pH that's exactly the same as if you ignored water's contribution because they're so different from one another. But in this example where they're similar, we can't make any approximations to solve for this. All right, so there we go, common ion effect. Put acid in water, it should be acidic. Okay. So other ideas of common ion effect is really just Le Chatelier's principle and using your intuition a little bit. If we have a system that's already at equilibrium, we can disturb it a little bit and predict what has to happen, especially to the pH if it's a weak acid solution. So let's consider water. All right, here's the KW of water. Let's think about what happens. If we add H plus to pure water, what do we think will happen? Will it become more acidic or basic? Acidic. But let's use KW to predict that. All right, we start with pure water. It starts at its like regular KW equilibria. So if we're adding H plus, we're adding a what? A reactant or product? A product, yeah. So just think Le Chatelier's principle. So we add a product. Which way does the reaction have to shift if we add a tiny bit of H plus? Shifts to the reactant side, so it shifts this way. All right, so if it shifts that way, remember, with shifts, change happens. So the shift is actually the change line in your ice table. So pretend that we made an ice table, and it shifts in the reverse direction. In the change line under water, what will we put? Plus X or minus X? Plus X. And then what goes on the other side? Minus X, yeah. So what does that mean? How does our pH change here? So if the reaction's moving in the reverse direction, we're going to make a little bit more water, but we're going to consume a little H plus, but we're also consuming a little bit of hydroxide. Right? So what we see here is that, from initial conditions, hydroxide concentration actually goes down. And so if the hydroxide concentration goes down, how does the pOH change? It goes up. And so if hydroxide goes down, pOH goes up, how does the pH change? Goes down. And what does that mean when your pH goes down? It gets more acidic. Yes, it gets more acidic. So see how using Le Chatelier's principle, common ion effect, and shifting also matches our intuition. You add acid to pure water, it becomes more acidic, but really it's because you're disrupting your KW, or your water equilibrium. All right? Okay, so let's do one more. When we add sodium acetate to an acetic acid solution, all right, so here is the Ka expression for acetic acid. This time we're adding sodium acetate. What's consumed? How does the pH change? All right, so sodium acetate is what? An acid or a base? Acetic acid is a acid, so sodium acetate has to be a base. Yeah, so this is a base. So if you add a base to water, the solution should do what? Become more basic. So let's see if Le Chatelier's and the common ion effect agrees with that. So right now we have acetic acid in solution. It establishes this equilibrium, but we're adding sodium acetate to this thing already at equilibrium. So what are we adding? A reactant, or are we adding product? We're adding the product, because remember, this is the weak acid. Here's its conjugate base. So we are adding the conjugate base. We're adding this. So Le Chatelier predicts the reaction goes which way? Reverse. So this also predicts the change line in our ice table. So we should gain a little bit more acid, but consume a little H plus and consume a little bit of that base. And so what I want you to focus on is this H plus. Right? When we add conjugate base, when we add product, we shift the reaction in reverse. The concentration of H plus changes how in this reaction? It goes down, right? Because we consume a little bit of it. So how does the pH change? Goes up, yeah. If the H plus goes down, because we shifted the reaction in reverse, so we consume some of the products, make a little bit more reactant, pH goes down, or sorry, H plus goes down, therefore pH goes up. So this solution becomes more what? Basic. And does that match our intuition? We add a base to solution. Yep, the solution comes more basic. And it's because we're disrupting these equilibriums. So that is the idea of the common ion effect, that we're just adding things already at equilibrium, all right, to solution, predicting which way it shifts, but also connecting that to how does the pH have to change. But it's always going to match your intuition. If you add an acid to something, anything, it's always going to become more acidic. If you're going to add more base to something, it's going to become more basic. But understanding how it connects to the equilibria is important too. Okay, so this is putting everything together. So I mentioned that in chapter 16, we put just a weak acid in solution, calculated the pH. We put just a weak base into solution, calculate the pH. But now we're going to talk about buffers. A buffer is when both the acid and its conjugate base are present in large quantities in the same solution, right? So let's just review a little bit. So pretend we have acetic acid, right? In chapter 16, we just put acetic acid into solution, just HA. That was the only thing in there. And we just did an ice table, x squared over 0.1, but we were able to, do an approximation just fine. We set that equal to Ka because acetic acid's an acid, calculate H plus, get pH, right? In chapter 16, we also looked at, okay, well, what if I put the conjugate into water? Right, so sodium acetate isn't an acid, it's actually a base, so we need to use Kb. We can go ahead and approximate just fine. X is equal to hydroxide concentration because we used Kb, we get POH. So now, in this chapter, all right, in chapter 17 is, okay, well, what if both of those things are present in your solution in very large quantities? That is a buffer. You have both HA and A minus, both of them, like large mole amounts of both of them in the solution at the same time. So this is a buffer, all right, where you have your weak acid and its conjugate base in large quantities, or remember, we can have a weak base system. So you can have a weak base and its conjugate acid present in large quantities at the same time, right? So buffers are great. Our bodies, I call affectionately call ourselves like big water bags, but technically, if I want to be more specific, we're actually big buffer bags. Our bodies are just big buffer systems, because the idea is like you drink a little bit of soda. Soda is acidic, but when you drink it, the pH of our body doesn't change drastically, and that's because there's lots of buffer systems in our body to resist those small changes in pH, right? So we're going to show a new equation here to calculate pHs of buffers, but you need to be able to recognize that it is a buffer, and that's the most important thing here. So I'm going to introduce the equation, the Henderson-Hasselbalch equation, where you calculate the pH of a buffer, where it's equal to the pKa plus the ratio of the base and the acid forms of that's present in your buffer. All right, so this is a very calculation-heavy chapter. Okay. So let's do some calculations. Okay, so pH of 0.1 molarity acetic acid. Tell me what the pH is. And I give you the Ka, it's right there, 1.8 times 10 to the negative 5. Do you need to do a full-blown ice table at this point? No. What is this going to turn into? Ka, which is 1.8 times 10 to the negative 5, equals what? X squared over what? 0.1, okay? X is equal to, what did I get? Boom. 0.00134 molarity, but that's the concentration of what? H plus. Perfect. So then you pH that. Of course, we use the approximation 2.87. So cool. You put acetic acid in solution, the solution should be acidic. Perfect. Okay. So now we'll do exactly what we kind of proposed earlier, the common ion effect. Okay. So we're starting with this 1 liter of acetic acid solution, but now we're going to add 1 mole of sodium acetate. Calculate the new pH. So what is our intuition state? We're adding what into water? Sodium acetate. Sodium acetate's a what? Base. So the pH we calculate should go up or down? Up, because we're adding a base. So let's see if that happens. All right. So let's set this up. All right, so remember, in our ice table, we always start with concentrations. So I initially start with 1 liter of 0.1 molarity HA. So this is 0.1 molarity HA. But we're adding sodium acetate into solution. We want to predict which way this solution shifts. So what we want to do is calculate, okay, what is the concentration of sodium acetate initially? If I put 1 mole in 1 liter, what's the concentration? 1 molarity. And so that value is going to go in the initial line as well. All right. Just kind of like how we did that weak acid, the very, very dilute HCl solution. Right? Both of those things are at the solution at the same time. There's no H+. Which way does this reaction have to go? Forward, because we need to replenish some of that H+. All right, so at equilibrium, we have 0.1 minus X of HA. We have X amount of H+, and then we have 1 plus X of A minus. Perfect. All right, what's the trick with ice tables? What do we always do? Put the E line into K, right? So our Ka expression is simply H plus concentration, conjugate base concentration, HA concentration. Again, all of these are at equilibrium. And so this is our E line. Everything in our E line goes into the Ka expression. So we get that Ka equals X times 1 plus X over 0.1 minus X equals Ka. I give it to you as 1.8 times 10 to the negative 5. All right. Does that look easy to solve? No, it does not. Do you think there's an approximation we can make? I sure hope so. Okay, what approximation do you think we can make? So this X value, is it going to be a big number or a small number? Is it going to move forward that much? No. K is really small. All right, so it's not going to move forward that much. So 0.1 minus X, that minus X is going to be what? Really Small, yes, this is going to be small. So can we get rid of it? Yes. Is there another x in this equation that's screwing us up? Yes, the top one, right? But let's think about it. You already told me plus x minus x is going to be really small. So if you subtract a really small number from 1, is it going to change 1 that much? It's not. So we can also say that top plus x is very small, so we can ignore it. So here, for a buffer, we're actually making 2 approximations. We're going to say both the plus and minus x are very small. And so this equation simplifies to x times 1 when we approximate over 0.1 equals 1.8 times 10 to the negative 5. Does that look hard to solve? No, not at all. And so, yeah, go ahead and calculate. X is equal to something like 1.8 times 10 to the negative 6 molarity. X is the concentration of what? Hydrogen, H+, perfect, because that's what the ice table says. And so when you negative log that, you get a pH of 5.7. So I ask you, you add sodium acetate, a base, to water, the solution becomes more basic. Did our solution become more basic? Yes, it did. Okay, perfect. So we just use the Ka expression and 2 approximations. We're just saying that the plus x, minus x here's are really, really small. So what the Henderson-Hasselbalch equation is we just use that approximation, right? I just set this back up where that plus x and minus x, we end up approximating it, all right? So what we see here is that 1.0, that is our initial concentration of A minus. 0.1, that is our initial concentration of HA. That was given in the question, all right? So here, this is, HA concentration initial. This was A minus concentration initial. So we're just saying that plus x and minus x are really small. We can just go ahead and say equilibrium concentrations of the conjugates are the same as the initial concentrations of the conjugates. And so what this different equation is, pH equals pKa plus log base over acid, is the Ka expression with the approximations already made, where you just negative log both sides of the Ka expression. So that's all that Henderson and Hasselbalch did. They just took the Ka expression and negative logged both sides, rearranged it, and called it a new expression and named it after themselves. That's all they did. All right. So this equation we use for buffer systems, but again, use this equation with caution, because we're making an approximation where we're getting rid of that plus x and minus x. Where this equation does not work is for very, very dilute buffers, but that's outside the scope of this class, right? So this base to acid ratio will typically always be those initial concentrations that come from the information given in the question, all right? So lots of calculations that we'll explore using this equation, where notice how it's concentrations of base over acid, but as long as the buffer is in the same volume, it's the same solution, we can also do that base to acid ratio. It can also be in the unit of moles. So if you know how many moles of B you have, and you know how many moles of A you have, if they're in the same volume, you don't have to convert those into molarity. And so I'll show you some tips and tricks to make these calculations faster. As long as you know it's always the base to acid ratio, again, as long as the volume's the same for both of them. Okay, so we'll do one question. We'll just do this slide and exploring the Henderson-Hasselbalch equation to see if you can plug everything in. Okay, so here's our Henderson-Hasselbalch equation. pH equals pKa plus log base over acid. So what is pKa? I didn't give you pKa. I gave you Ka. What is pKa? Negative log of that number. So if you go ahead and negative log 6.6 times 10 to the negative 4, you get that the pKa is 3.18. Perfect. Okay. So let's calculate the pH of a buffer that is made by mixing 0.15 moles of HF and 0.5 moles of NaF. So together to form 1 liter of solution. So the concentration of HF is 0.15 moles over 1 liter. So its concentration is 0.15 molarity. What is the concentration of F minus? 0.5 molarity, yeah, because it's 0.5 moles in 1 liter, right? So these are the concentrations that I'm going to put into my Henderson-Hasselbalch equation. But HF is which component, the acid or the base? It's the acid, yes, it's the acid. F minus is which component? The base, yes, because it's the conjugate base. So we have all the information we need to plug in these values. So pH equals pKa, 3.18 plus log base over acid. So it's 0.5 molarity over 0.15 molarity. And we get that this pH is something like 3.70, right? So notice how, yes, it's base concentration over acid concentration, but notice how we calculated those concentrations. We divided by the same volume for each of them, all right? So regardless of putting these concentrations base to acids in molarity, we can also just keep them into moles and save ourselves that step of dividing by concentration twice when it just cancels out in the end. All right, so we'll stop there, do more buffers, Henderson-Hasselbalch calculations on Thursday. I suggest getting a head start on Chapter 16 homework. If you haven't already, it's a long one.